Hi there. In this section, we're going to keep going in Chapter 4. And I put a little note / sort of guidepost here for you at the beginning. So the idea is that Section 4.2 is probably the longest section that we do the whole semester. I'm not going over everything in the section because a lot of this stuff is repeated from Appendix E, which we did cover, and Section 4.1. There's a lot of repeat stuff. So you guys do have a lot of homework in this section, and I'm still not even putting a lot of the stuff that I could put in the homework. I think you have 19 homework problems, and some of these problems do take a long time. So I'm going to go over 6 examples in this video, and you'll see it's a wide variety of stuff. So anything that's already been covered earlier in Chapter 4 or in Appendix E, I'm not going back over. You're expected to know it. Alright, so I'm going to briefly go over some of the lecture notes here, and then I'm just going to get right into the examples just to keep the video under 40 minutes. So the idea is, this is what we saw in 4.1. We saw that we have these xi stars that are just any points in the subintervals. And when we take the limit of the sums of the areas of these rectangles, that gives us an area, right? And that's how we did problems in 4.1. So even though theoretically there's a lot more going on behind the scenes, on a lot of levels, it's just too hard to explain. Because we really can't do a lot of proofs. And I'm not going to go over something that's deep and theoretic without being able to prove it. So instead, I'm just asking you as a student to sort of determine whether the ideas are believable. So at the end of this video, I'm going to go over some of these concepts with some technology. If you already are pretty much on board with what's been going on in Appendix E and 4.1, should be fine. If you're still kind of mixed up, make sure you stick around for the video at the very end. There's just going to be a little thing at the end. So what we're going to do is take that sum that had the xi stars, and we're going to call it a definite integral. We're going to give it a new name. For those of you who have already taken calculus or looked way ahead, the word integral later on will mean something slightly different. But just remember, if it has the word definite in front of it, this is what it means. Okay, so the word integral by itself has a meaning. If you put the word definite in front of it, it has a slightly different meaning. So just keep that in mind as we progress through the semester. So that big sum that we saw in the previous slide, we're just calling it this thing. Okay, so if this limit exists, then whatever that limit is, whatever that number is, we're going to call that thing the definite integral from a to b of the function, whatever the function happens to be, right? And again, our function is just some function defined on some interval. So the hardest part about this stuff is just flat out getting grips on the notation and the algebra. So I'm going to show you a problem that looks like something we did in a previous video. Lots and lots of algebra. So this is all stuff that you guys can read. I'm not going through the definitions and the history. I'll let you guys read that. I do want to talk a little bit about this. This is what I'm going to go over at the end of the video. I'm going to explain this precise meaning of a definite integral. So again, it's an epsilon proof. And it's basically saying that as the number of rectangles increases, So yeah, look here. So we're saying epsilon is some finite value. So epsilon is just the difference between the function itself and the rectangles. And we just take the absolute value. Because remember, epsilon has to be positive. So for every acceptable error, again, if you want to think of epsilon as meaning error, for every acceptable error, we can find some value of n bigger than some set number. And for every choice of xi in each subinterval, this statement is true. So where we left off at the beginning of the last slides, even though we didn't do any work with it, because again, a lot of this work is just very, very hard. So I'm just asking that you just remember sort of the concepts. The idea here is that where we left off is we said that you can pick xi anywhere in the subinterval. And what we did, as you recall, for the big example we did, example 5, I did a right point approximation where all of the approximations were overestimates. And then I could have done a left endpoint approximation where all of them were underestimates. Well, if your approximations that are all too big, if all those errors go to 0 and all your limits that are too small, all those errors go to 0, then that shows you that no matter where you pick the number in the interval, it's going to, the error, so the amount of difference between the function and the approximation, is going to go to 0. There's a lot of big, deep concepts going on here. For those of you who like to just whip through homework and look stuff up on the internet, you need to slow down when you get to this stuff, because I can ask questions on a test lots and lots of different ways. Again, you're going to see 6 examples just in this video, and I'm not even covering every type of problem that's on the homework or in the book. I'm only going over a few of the major ones. Alright, so the next thing I want to look at is, we can skip that, you guys should read it, I'm just not going over it, is simplifying calculations. So what we saw in 4.1 is that it doesn't matter if we use a left endpoint, right endpoint, or midpoint approximation. They all converge on the same limit value if the limit exists. So it turns out that that's always true. It's hard to prove, but it should be believable. Again, if you're still like, I don't really believe it, watch the video at the end, at the very end of this one. So what we're doing is just from this point forward, even though theoretically these should have xi stars on them, we're allowed to pick any point in the interval, and the definitions require that this is true for every point in the interval. Because we're only doing a few basic calculations, we're just going to call everything a right endpoint. So our definite integral calculation, definition actually, changes from this with an xi star just to this with an xi. And then we can bring back this stuff that we used in 4.1. So I am going to do another one of these. I'm going to show you how it works again, but I'm not going into the theory behind this that's been established earlier. Alright, so what we're going to do now is just practice working with Riemann sums a little bit. I'm not putting a lot of time into this, just showing you one example, and then you got to figure it out on your own after that. So look at what we have here. I need to use this definition to turn this expression into a limit of Riemann sums. So I want to use this delta x formula, and I want to use this xi formula. Alright, so that's what we do first, right? You identify a and b. That's easy to see from the integral notation. A is on the bottom, b is on the top. There's my function. That's all given in the problem, right? Now I need to compute delta x and xi. So delta x is just b minus a over n, so it's 2 over n. Remember, we're not using xi star. We're just allowed to pick any xi star, so we're going to use xi. That's just a plus I delta x. A is 1. Delta x is 2 over n. So we get 1 plus 2i over n. Now we plug everything back into the formula. So this formula is previous slide. It's just the limit as n goes to infinity of f of xi, so this is xi, times delta x. So some things about notation that are goofy, you just got to deal with it. This is f of, so this whole thing is saying that this is a function where this is x, or xi. This is multiplication. So this parentheses means f of, and this means multiplication. So even though they both use parentheses, they have different meanings. Now you just plug everything in. So here's our formula. So anytime we see xi, we just plug it in here. So we have an x to the 4th, so we plug xi in here and get this to the 4th. 1 minus x to the 6th, plug in xi. And again, this is still multiplied. And that's the answer, and you're done. So, if this is a test question, you absolutely cannot FOIL this out or expand it. You will be there all day. This is the answer. Do not simplify. Some of you guys out there are really bad at following basic directions. I'm telling you this for your own good. Follow the directions on a test. If this is a test question, this would be like 8 points. Okay? I need to know that you guys can do the basic stuff. That's the answer. And you leave it. Now, let's do the opposite of that problem. What if you're given a Riemann integral? Again, these could be xi stars, right? But we're using xi's because we're just using right endpoints for everything. How do I turn this into a definite integral? Well, a couple of things. Because we have this limit here, right? Remember, delta x erases the information of your interval, right? So delta x is b minus a over n. So it would just be pi over n. But we don't know what that means. Is that negative pi to 0? Is that 0 to pi? So we have to be told what the interval is. Remember, when you set up these expressions, it kind of like, you kind of lose some information. Well, let's look at it and see if we can figure it out. So we're trying to turn it into, let me go back, we're trying to turn it into this, right? So we're given this, we're trying to turn it into this. Well, we know a and b, that's the farthest left value, that's the farthest right value, and we know f of x, because we're given f of xi in the problem, so f of x is just whatever we see without an xi, right? So let's go back and see what that looks like. Right, so here's a, here's b. Now we were given f of xi, but we just want to turn that into an f of x. So all you do is just take the i's off the x's, right? So we just want to turn this expression into this one, right? So it's just 0 to pi, xi cubed becomes x cubed, xi sine xi because x sine x. Tack on a dx, and you're done. That's the answer. So even though we are never going to evaluate the one on the previous slide, we would never evaluate this Riemann sum. It's too hard. But real soon we're going to learn how to do this. In Calc 2, actually real early, you learn how to do x sine x. So this is actually, for us, even too tough of a problem to solve. But that's not what I'm interested in here. I'm interested in, can you guys conceive of what's going on? Can you set it up? Are you being organized and that sort of thing? That's what I'm testing you on. Anybody can use a calculator. Anybody can use, product rule, quotient rule, and that kind of stuff. It's much more challenging to prove to me that you understand the material. And that's the way it should be taught. All right, let's keep rolling. So here's your formulas for evaluating your integrals. You guys should know those. All those were proven in Appendix E. Here's some formulas that we're going to use. We already saw these formulas before. Again, I just put them in here so you had them handy. They're very, very easy. I did not prove them. So let's go ahead and do one of these. So we're going to use a Riemann sum to evaluate this definite integral. So I'm just going to say it right now. A lot of you guys on exams are using unapproved methods. If I say on a test to use a Riemann sum and use anything else, you're going to get a 0. And on a test, if this is a test question, this is worth anywhere between 15 and 20 points, which is a monstrous amount of points because your tests are only 150 points each in a 1,000-point class. So you have to learn how to do this. This is worth a bunch of points. I did one of these in 4.1. I'm going to do another one now. All right, so the first thing you do is you need to set everything up. You need your delta x. You need your xi. Right? Because we're going to be converting this into a Riemann sum. And it takes a while. So here's A. Here's B. And then we just rewrite this with xi's. And this becomes delta x, right? All right, so b minus a over n, 9 minus 1 over n, so it's 8 over n. Now we need to figure out what our xi's are. Well, that's a plus I delta x. We just found delta x over here. And you simplify everything, you get 1 plus 8i over n. Now we plug everything in. So we're just converting this straight to a Riemann sum. All I did is replace the function with its xi version. Now I'm going to convert delta x, and I'm plugging in the xi's. So so this is just the generic setup, right? This is just f of xi, and this is just delta x. Now everywhere I see an xi, I replace it with this. So here we have an xi squared. So we put in, here's xi, it's squared, minus 4 times, here's an xi. I pull this, put it in there. And then I replace, so 6 stays 6, and I replace delta x. Okay, so let me point out something, guys. The way I do these problems is a little bit different than the way that the solution manuals do it. Either way is fine. My way is more steps, but it's harder to mess up the algebra. I highly recommend you do the problems the way I'm about to show you. If you are not amazing at algebra, you can't afford to make a mistake, or you will not get the right answer. Do not spend hours and hours doing these problems, guys. Learn the technique, do it once, and get it right the first time. There's no reason to be in a big rush, because these problems take 10 minutes to do anyway, and if you mess it up, you got to do it twice. So take 10 minutes and just do a longer method like I'm about to do. So what I'm going to do next is I FOIL everything. I just distribute all these squares, distribute all the negatives, right? Next step, I actually distribute the 8n and combine like terms on the inside. So that's where I do it a little different than the solution guides and some of the internet stuff. The internet stuff pulls the 8n to the front, but man, it's really easy to mess that up. If you pull this 8 over n to the front, it's really easy to forget that that distributive property is still going on. I'd much rather distribute it now. And that way I don't have to think about it. Now I can just use properties of sums for the rest of the time. I don't have to remember the distributive property. It's done. Okay, so you should be able to see the steps, right? So this step here, I just squared this, and then I distributed, right? And this is all positive, and this, you have to distribute the negative. A lot of you guys were missing that on the tests. You guys can't forget to distribute negatives. If you got to draw the little rainbows or whatever, draw the rainbows. Then I combined like terms. So here I have like 1 minus 4 plus 6, which is 3. 3 times 8 over n is 24 over n. So all I'm doing is just simplifying and distributing. I'm not showing every step, but I'm showing enough of them. Next, well, let me go back to the end of this one. You can see what we're going to do next. Next, we're going to take this sum, and we're going to push the sum as far to the right as we can inside. So we have properties as sums. 512 over n cubed is a constant as far as this sum is concerned. So I can push this sum. I can basically make 3 copies of the sum. I can distribute the sum. And then I can push it right up next to all of the indexes, right? So this, just in case you guys are wondering, anytime you see a limit, the limit assumes everything after it is in the limit, okay? You don't mix up limits with non-limits, okay? So this whole thing is inside the limit. So I just pushed all the sums right up against I squared, pushed it up against I, and pushed it up against 1. Now I have formulas for I squared, I, and 1. I plug in the formulas. From here, this is what I did. I canceled all the constants and pulled the constants out. So 512 over 6 reduces to 256 over 3. 128 over 2 reduces to 64. So that's the same thing I did last time I did a problem like this. Take the constants, pull them to the front. Then take these ends and kind of push them up inside all the little pieces. I've seen in the past a lot of people want to distribute this. There's no reason to, guys. You're trying to get stuff to cancel. The best way to get something to cancel is to factor it. Well, this is already factored, so don't distribute this. Just leave it the way it is. So I took this n cubed, I put 1 here, and 1 here. Now this is going to simplify real nice. Same thing over here. I have an n and n plus 1 and an n squared. I'm just going to give one of these n's to each of the terms. And these two cancel. So if you see right away that it cancels, just go ahead and cancel it. So these two n's cancel. Now I'm going to simplify it one more step. This n over n is 1. It's about to go away. I just push this n up. This is 1 over 1 plus n. Push this one up. This is 2 plus 1 over n. N over n becomes 1, and this is the same as this. And now I take the limit. So this 1 just went away because it's multiplied. Here we have 1 plus 0. This is 2 plus 0. This 1 went away. This is 1 plus 0, and this stays 24. Simplify as much as you want to or as much as you can. Once you have a bunch of numbers written down, you don't have to show any more work. But here's the thing. If you're doing this on your calculator, you might get a decimal. You cannot put a decimal answer in on the homework. It will not accept it. You must write this as a fraction in lowest terms. On a test, I'm going to require the same thing. Because there's other ways to solve these, right? You have to show every step that I've shown except the arithmetic. Okay? Now, if you want to combine some steps together, that's fine, but it has to logically make sense. I have to be able to read it and see, oh, there's a chain of logic here and it works. If you're doing anything else, you're not going to get points. And I think that's been pretty well established in the class up to this stage. So that's it. Again, about a 10-minute problem if you know what you're doing ahead of time. Okay? Some of the problems in Calc 1 get pretty long. For those of you moving on to Calc 2, there's a couple problems in Calc 2 that take about 25 minutes. And differential equations, same thing. And that's knowing the answer. That's just like running the steps, like this. All right, let's move on. Next up is just a bunch of properties. So I'm going to let you read the properties. If I were you, I'd memorize them, because you're going to use them. So let's just jump right into example 4. I'm going to show you which properties we're using. Oh, let me point something out real quick, sorry. These two properties don't have names. I don't know why they don't have names in your book, but you use them a lot. So this one is just, if you reverse the a and the b, it just makes the integral negative, the definite integral negative. We're actually going to use that. And if a equals b, so the integral from a to a is always 0. So this, watch for this. These actually are used quite a bit. This, well, actually, both of these properties are used in a proof in the next section, and it's definitely the hardest proof we do all semester, but you absolutely have to understand it. You need these two properties. All right, so these are pretty easy. Let's go through these, just make sure we generally understand what they're saying. Because these are sums, right? Think about what this is saying. This is the sum of, just a constant, right, over an interval. Well, if your function is a constant, it's a horizontal line. But we've defined the definite integral as the area between the function, two vertical lines, and the axis. Well, that's a rectangle. This is just the area of a rectangle. This is the base, and the function is the height. Okay, so this is just a rectangle. These other ones are just properties that we've seen with sums. So because we're defining definite integrals as limits of sums, limits have this addition property, sums have this addition property. So we're just saying that if the limits exist, we can use our limit property or our sum property, and it becomes an integral property. Or in this case, a definite integral property. Here, constants can be factored out. That's just similar to this one. And we can distribute through minuses. So this one is very, very similar to this one. So these are properties 1 through 4. Let's see how to use these properties. So you can be asked these sorts of questions lots of different ways. So this is just a decent example of using properties instead of using the Riemann sums. So we could do Riemann sums with this, like we did in example 3. But remember how big example 3 just got humongous, right? Is there another way to do it? Well, we can use our definite integral properties, right? So what you want to do is just push this thing, use the properties, right? So I'm using properties 2 and 3. So let's go look at properties 2 and 3. This is saying if you have a sum that you can take two different definite integrals connected by that sum. And 3 says if I have a constant, I can pull that constant to the front. Okay. Oh, and oh yeah, we're going to use the other one in a second. So that's what I did. I saw a sum, and I said I can just split this into two integrals. And for this one, I can pull the constant to the front. So this one has a 3x squared. I just pulled that 3 to the front. Now we need to have different ways of solving problems. So we're going to look separately at the two definite integrals on the right side. We're going to look at this one first. This one, we're just using definite integral property number 1. This is a function y equals 4. This is a horizontal line. So we're just finding the area of the rectangle bounded by y equals 4, x equals 0, x equals 1, and y equals 0. That's a rectangle. Here's the base, b minus a. Here's the height, which we were calling c in the property list. It's called c. Well, that's just 4. So the area of this is just 4. Okay, that's pretty good. Let's look at this second one. This is 3 times this integral. Well, this integral from 0 to 1 of x squared, we computed this earlier. We know that it's 1/3. So anytime you compute an integral and you just know the value, again, we're saying like within like a certain context, right? Here within the class notes, my point is that I can give you the value of a certain piece of an integral, and then you use properties to rebuild it, and that's what I'm doing here. So we know this is 1/3 because we proved it together, and it's 3 times 1/3, which is 1. So we know that this is 1. And then you go back and just add it up. So the sum of these two things is just the sum of the individual values, which is 5, and that's the answer. So this happens a lot on the homework. Again, these questions can be asked a lot of different ways. You can be given like pieces, parts, values, and have to use combinations using those properties. If you're doing these problems any other way, you're going to be unhappy when the test comes around. Because I will tell you guys, the stuff on the test looks like the notes. I'm going to say use properties of integrals. If you like use some integral property, some other thing, I'm going to pick problems that look like these. So you got to keep track of what section we're in, what the homework looks like. I'm going to try to reuse a lot of those problems. I mean, they're not word for word, but conceptually they're the same thing. All right, let's keep rolling. So next up, we have property 5. Property 5 is very nice. This says we can add or subtract definite integrals. So this is saying, so this is different than what we saw back here. What we saw back here is that we were splitting the integral across the sum. This property is telling us something different. This is telling us if we want to find an overall definite integral, we can break it into vertical sections, like chunks. Right? So look at the limits. So here, the definite integral from a to b is this entire blue area. But that's this area plus this area. So that's the area from a to c plus the area from c to b. So this comes up a lot when we have to show that we can compute a larger integral by breaking it into smaller bits. So let's see how that works. All right, so we're going to use the graph to estimate the following definite integrals. So you have a problem similar to this on the homework. What I'm showing you guys is a slightly different version because I just want to point out some other things that are earlier in these notes, but I didn't go over just because I'm trying to keep the videos kind of short. So let's jump in. All right, so the first one, we want to find the integral, definite integral, from 0 to 16 of f of x dx. So that's this. And you look at it, and you might not know what this shape is. It turns out it is a trapezoid. It's just a trapezoid on its side, right? So the area of a trapezoid, I just called it A1. You can call it whatever you want. So the area of a trapezoid is 1/2 big base plus little base. Remember, a trapezoid has two flat sides, or flat top and bottom, or two flat sides. Height here is actually the width, but I'm just using the formula the way it appears. So it's 1/2, so 24, that's our big base, 24, plus 8 is our small base, times 16, which is our height. Again, it's on its side, so it's 256. So here we're using just a geometric property of the definite integral, right? Definite integrals are areas. You're allowed to compute this area any way you want. Okay? Some areas are better than others. All right, let's look at the second part here. The area from 16 to 24, so the definite integral from 16 to 24. That's a rectangle, right? You can see what part it is, just that little part right there. Well, a rectangle is just base times height. This time the base is horizontal, it's 8. The height is 24, so it's 192. Now, part C is a little bit different, right? So part C, we're going from 24 to 56. And you can see what's going to happen, right? So 24 to 56, the definite integral, is two triangles. How do we do two triangles? So what you have to do is you have to use the sum property. So ideally, we'd like to just add these two areas together. But earlier, I didn't go over it, but you guys can read it. Hopefully you're reading these PowerPoints before you're watching the videos. This area is, well, the function here is negative. Okay, so look at what we have here. We have the area from 24 to 40. That's this blue part, right? Look at it. That's that blue part right there. I'm calling that A3. It's just 1/2 base times height. So it's 1/2. The base is 16. The height is 24. So it's 192. This other triangle is actually the same size, right? So everything's exactly the same. But we can't add these together. Because the function is negative down here, we have to subtract the area. This is how we define integrals as we move from left to right. So the area itself is not negative. Areas are always positive. But if the function is below the x-axis, then we subtract the area. So instead of adding these two areas together, we actually subtract them. So you can think of it as like A3 plus negative A4. Okay, so again, the areas themselves are positive. However, the rule says that we're just going to subtract the value of the area because the function itself is negative. So I know you guys might be thinking, wait a second, but the height can be negative. True, but the way area has been defined, we have to be consistent with mathematical definitions. We can't just start renaming stuff just because we feel like it. Okay, so it turns out this area, so both of these areas are positive 192, but the definite integral from here to here is 0. Okay, because of what it represents, the areas, what it means, right? It's consistent with the definitions we've established. So that's easy to remember. I just don't want you to think that the area is negative. It's not. Okay, so we got a few more properties. These are inequality properties. And the first 5 we saw, it doesn't matter what the relationship is between A and B. But these are comparison properties that only work if A is less than B. So that we have to move from left to right. Okay? Or it can be equal, because then everything's 0. So this says if your function is positive, then the definite integral is positive, or 0. That's really, really important, right? Think about it. So if your function never takes on negative values, then the definite integral can't take on negative values. That's a really nice property. You're going to use it on the homework and maybe on a test. Number 7, if a function is bigger than another function, then the definite integral is bigger than the definite integral of the other function. So this one is just, we can just use this by extension. We could subtract g of x from both sides and it just turns into this. Okay, so this is easy to prove. I'm not going to prove it, but it is easy to prove, and if you prove number 6, then number 7 is easy. So 6 and 7 are easy to use. You guys are, if you're moving on to Calc 2, you're going to use those two properties a bunch in Calc 2. Number 8 is the harder property to use, so this is the one we want to talk about the most. So if little m is less than or equal to f of x is less than or equal to capital M, then you have this whole thing. What is this? So I'm going to show you a picture of this, and I think it's going to make this easier. So what that property 8 is saying is that if you build a rectangle out of the maximum value of f of x on an interval, and then you build another rectangle using the minimum, that the area, so the definite integral of the function, has to be smaller than the big rectangle and bigger than the small rectangle. So that's what this is saying, right? Because this is a rectangle, this is a rectangle. We're just saying that the definite integral of the function, bigger than this, smaller than this. All right, let's see how to use it. So I have to find the absolute max, I'm going to call it big M, and the absolute min, little m, for my function on the interval, right? This is given in the problem, right? Because look here, this is A, and this is B, and this is my function, right? So all this is given. So how do we find an absolute max and an absolute min of a function on an interval? Well, we have to use the techniques from chapter 3. We have to take the derivative, find the critical values, plug in the endpoints and the critical values, and compare everything. Luckily, this is a pretty well-behaved function because f doesn't have any critical values on the interval, which is really, really nice, right? So this derivative is never 0, so no critical values there. And the only place you get a DNE is when x equals 0, which is not on the interval, so we're safe. So that means the absolute max and min have to be the endpoints. And we just plug in, there's only 2 endpoints. One of them has to be the max, one of them has to be the min. So you just plug the numbers in and you see that f of 1 is a min, f of 4 is a max. So that means that 1 is now our, well, let me show you the formula. So here's the formula. So 1 is this number, so you just plug everything in. This is 1, this is 4, this is 1. This, you just plug in with the definite integral. This is the maximum, so this is 2, 4, and 1. Plug everything in. Compute. All right, this is very easy arithmetic, and it turns out you're done. That's the answer. So this is another excellent example of the type of question I can ask on a test that only requires derivatives. And on the homework, you have 2 problems. One of them looks just like this. The other one is similar to this. I highly recommend you follow this template. If this is a test question, you have to show that there's no critical points, okay? Because if there are critical points, one of those critical points could be a maximum, could be a minimum, and then you'll get different numbers for the either little m or big M. All right, well, that's it. I do want to show you that thing I promised was going to be at the end, so let's go ahead and do that. Oh, we're at 40 minutes right now. So if you guys have had enough video for one day, which I totally understand if you have, Don't worry about the rest of this video. This isn't going to be on a test or anything. What I'm doing, let me show you what I'm going over here. I'm going over why this makes sense. Let me find it right here. Okay. I'm going over why it reset. Let me find it again. Here it is. I'm going over why this makes sense. Okay. So I'm just going to use this function 0.2x squared. So this is in the Explore It in your homework. And what I'm going to do is I'm just going to pick, I don't know, 5 rectangles or something. Let's do right endpoint. What we got here? 4. 4 is fine. So look at what we have here. I'm just doing the right side, right endpoint approximation. And let's look at what's going on here. So this thing gives us our error down here at the bottom. Do you guys see it? It's way down here at the bottom. So here's the idea. Give me an error. Just pick a number and say, can you get the difference between, so the absolute value of the difference between this red part, which is the actual curve, area under the curve, and the Riemann sum. So the Riemann sum is the green plus the red. So I can color it red. It doesn't make any difference. Okay, so right now it's just green, so it's easier to pick out. If you're colorblind, you're fine. So can we, and if we subtract, if you take this minus this and then take the absolute value, what we're looking at is just the green region, right? Because this red minus all of this red is just the green part. So let's say we want E to be, or epsilon to be 0.1. Can I find an n? So the difference between the net area, the net area is the real value of the definite integral, and the approximation is, so the rectangles, and then the difference is the green, so the subtracted part. So the error is the green. Can I get it less than 0.1? We'll just start scooting this to the right and watch the error go down. Can I get it less than 0.1? How far do I have to go? All right, well, I got to go bigger than 50. But you guys get the idea, right? Like, no matter what I pick, I'm going to be able to find some value, right? Because as you keep traveling to the right, the error gets smaller and smaller and smaller. Now, we can do the same thing with the left endpoint approximation, right? So here's the left endpoint. Now it's showing the errors as orange. Now the errors are negative. Again, we're just looking at the absolute value. How small can I get that error? All right, so that can get to 0.248. What about the midpoint rule? Right? Remember our good friend, the midpoint rule? Right? This is what it looks like, right? How small can I get that error? Well, because the midpoint rule alternates overestimates and underestimates, look how fast the midpoint rule error gets small. There, now I'm less than 0.1. I had to go 15 subintervals. Can I get it less than oh no, sorry. Now it's less than 0.1 right here. Oh geez. 5 subintervals, it's less than 0.1. Here it's less than 0.01. Here it's less than 0.001. So remember, when you're seeing an xi star, it's saying you can pick any value in the interval to find an approximation. And then this definition here, the precise meaning, says every choice in the interval. But we already know for a function like x squared or 0.2x squared, this is an underestimate. This is an overestimate. So if we can show that both of these values converge to the same number, then we've essentially proved this. Now, I'm not proving it, but I'm saying that that's what it would require. We'd have to prove that both of these lead to the same value. So that's what this means, that if this simulation went bigger than 50, we'd be able eventually to get that error all the way to 0. So this is in your ebook. You guys should check it out. Mess around with it. If you understand this precise meaning, if you feel that you're good on it, then you don't have to get in there and goof around with it. But I really think being able to change some parameters and move some stuff around, I think really does help kind of understand what all this stuff means. All right, so that's it for the video today. If you guys have any questions, let me put back up on the last page there. Shoot me a message or email me. And that'll be it for today. See you guys next video. Bye-bye now.